Somewhere out there, right now, in a galaxy wrapped in so much dust that no visible light escapes it, something enormous is sitting completely still, completely invisible, completely undetectable by almost every instrument humanity has ever pointed at the sky. It has been there for who knows how long. It gives off no light, no signal, no warning of any kind. It does not glow. And the only reason we know it exists at all is because, every so often, without any warning, it reaches out and destroys a star. In 2025, using the James Webb Space Telescope, a team of astronomers found several of these things for the first time in the history of astronomy, hiding in plain sight inside some of the dustiest galaxies we know of, completely dormant until the exact moment each one killed. This is the story of tidal disruption events, one of the most genuinely violent phenomena anywhere in the universe, and how the James Webb Space Telescope just revealed that they may be happening far more often than anyone realized, simply because most of them have been hiding somewhere no previous telescope could actually see. To understand what these things are, you first need to understand what a supermassive black hole actually does to a star that gets too close to it. Almost every large galaxy in the universe, including our own, has one of these objects sitting at its center. An object with a mass millions or even billions of times greater than our sun, packed into a region of space no larger than our solar system. The gravity around something that dense is so extreme that it does not simply pull a nearby star inward evenly. It pulls unevenly, stretching the side of the star closest to the black hole far more strongly than the side facing away. A difference in gravitational pull scientists call a tidal force. If a star wanders close enough, the tidal force becomes strong enough to overcome the star's own gravity holding it together, and the star is torn apart, stretched into a long, glowing thread of stellar material, a process astronomers have somewhat darkly nicknamed spaghettification. The star does not simply vanish in an instant. Over a period of days to weeks, it is drawn out into a stream of hot, glowing gas, wrapped partway around the black hole by its own orbital motion, before beginning to fall inward. About half of that shredded stellar material eventually falls into the black hole, superheating as it spirals inward and forming a bright, glowing disk of debris that can, for a brief period, outshine every other star in the entire host galaxy combined. A single dying star briefly producing more visible light than tens of billions of others put together. That entire sequence, a star's death, its debris, and the flare of light produced as the black hole consumes it, is called a tidal disruption event. Astronomers have been hunting for these events since the 1990s, and up until recently, they had found roughly 100 of them, almost all detected as sudden flares in optical or X-ray light, sweeping across relatively clean, dust-free galaxies where that light has an unobstructed path to reach our telescopes. Even before Webb ever got involved, the pace of discovery had already been picking up. In a survey using the Zwicky Transient Facility, a wide-field optical telescope in California built to scan large portions of the sky repeatedly for exactly this kind of sudden flare, researchers identified 18 new confirmed tidal disruption events in a single study, published in early 2024, more than doubling the total number of these events ever confirmed in the relatively nearby universe up to that point. That alone was a significant jump, suggesting these star-shredding events were considerably more common than the small handful known throughout the 1990s and 2000s had implied. But even that expanded count only covered galaxies, clear enough for optical light to escape freely. It said nothing about what might be happening in the countless galaxies too thick with dust for the same light to ever get out. That problem is dust. A huge number of galaxies in the universe are thick with it. Clouds of fine interstellar material that absorb and scatter visible light and X-rays before they ever have a chance to escape and travel toward Earth. If a tidal disruption event happens at the center of one of those dusty galaxies, the visible and X-ray flare produced when the black hole shreds its victim can be almost completely blocked, swallowed by the very same galaxy hosting the event, leaving astronomers with no way to ever detect it using the tools that had worked for every previously known case. For years, this meant an entire population of star-shredding black holes, potentially a very large one, was sitting effectively invisible, doing exactly the same violent thing to nearby stars as every confirmed case astronomers already knew about, just cloaked behind a wall of dust thick enough that none of it ever reached us in a form we could detect. This is precisely the problem the James Webb Space Telescope was built to solve, even if not for this purpose specifically. Webb observes primarily in infrared light, wavelengths far longer than the optical light our eyes can see, and infrared light has a critical advantage when it comes to dust. It passes through it far more easily. Dust that would completely block a visible light flare will often let a meaningful portion of infrared light straight through. In a study published in the astrophysical journal Letters in 2025, a team of researchers at MIT, Columbia University, and several collaborating institutions turned Webb toward galaxies specifically chosen because they were unusually dusty and gas-veiled, environments where a tidal disruption event would have been essentially undetectable using any of the methods astronomers had relied on for the previous 3 decades. They were not simply hoping to find a few examples. They were testing a specific hypothesis that an entire hidden population of star-shredding black holes existed in exactly this kind of environment, waiting for an instrument sensitive enough in the right wavelength range to finally expose them. It worked. The team reported the first ever James Webb Space Telescope observations of tidal disruption events, describing what they found in language astronomers do not use lightly, stating plainly that these events looked nothing like anything ever seen before. And what made the discovery even stranger was not simply that Webb had found tidal disruption events hidden behind dust. It was what the black holes themselves were doing beforehand. Every one of the black holes involved turned out to be dormant, not actively feeding, not glowing, not producing any detectable signal of activity at all, sitting completely quiet at the center of its galaxy for an unknown length of time, before suddenly flaring to life the moment a star wandered close enough to be destroyed. One of the graduate researchers involved in the study described it directly, that these had been quiet. Essentially inactive black holes doing nothing detectable at the centers of their galaxies, until they abruptly became active, almost as if waking up specifically to consume something that came too close. That distinction, dormant versus active, is not a small technical detail. Astronomers already know how to find active supermassive black holes. When a black hole is actively feeding, constantly pulling in gas and dust from its surroundings, it produces a steady, ongoing signature, radiation across multiple wavelengths that telescopes have been detecting and cataloging for decades. Those black holes announce themselves continuously, whether or not anything unusual happens to them. A dormant black hole does none of that. By definition, it produces essentially no ongoing signal at all, blending in perfectly with the empty space around it, right up until the singular moment it destroys something nearby. Before Webb's observations, there was no reliable way to detect a dormant black hole sitting inside a dusty galaxy at all, no signal to look for, no glow to trace back to its source. The only window into its existence was the brief, violent flare produced during an actual tidal disruption event. And until Webb's infrared sensitivity could actually punch through the dust surrounding these particular galaxies, even that narrow window was closed. Sit with that for a second, because it is the part of this discovery that is genuinely unsettling once you actually think it through. These are not black holes that announce themselves. They are not glowing, feeding monsters that astronomers can watch and track over time the way an active galactic nucleus behaves. They are silent, undetectable, indistinguishable in every practical sense from empty space, right up until the precise moment something wanders too close, and then, in a burst of light that can briefly outshine the rest of the galaxy around it, the truth becomes visible for exactly as long as the flare lasts, before the black hole goes dark and quiet again, waiting for whatever comes next. The implications of this discovery reach well beyond the specific handful of events the team actually found. If tidal disruption events have genuinely been happening at similar rates inside dusty, gas-obscured galaxies as they have in the clean, easily observed ones astronomers have studied for decades, then the true number of these star-shredding events occurring across the universe at any given moment could be significantly higher than the previous 3 decades of research had ever suggested. Entire supermassive black holes, potentially large numbers of them, may have been sitting completely undetected in dusty host galaxies this entire time, invisible, not because they are especially rare or especially far away, but simply because the specific method astronomers had been using to find them was blind to an entire category of environment where they happen to live. Some estimates in the broader field of tidal disruption research have suggested that dusty, infrared luminous galaxies could host a disproportionately large share of the universe's most massive black holes, precisely the kind of environment where a violent stellar death would have gone completely unnoticed until an instrument like Webb came along specifically capable of looking straight through the material hiding it. And the black holes hiding in dust are not even the strangest part of this larger picture, because in a separate, more recent piece of research, involving observations from both the James Webb Space Telescope and the Keck Observatory, astronomers confirmed something even stranger about where some of these star-killing black holes are actually located. In 2025 and 2026, researchers studying a tidal disruption event cataloged as AT 2024 TVD found that the black hole responsible for it was not sitting at the center of its host galaxy at all. It was offset, sitting roughly 8 kiloparsecs away from the galactic nucleus, a wandering supermassive black hole with no fixed home at the center of anything, drifting through its galaxy's outer regions until a star happened to cross its path. Follow-up analysis, published in June of this year in the Astrophysical Journal Letters, measured the black hole's mass at roughly 1 million times the mass of our Sun, genuinely supermassive, and found its mass came out to more than 3% of the surrounding stellar mass in that immediate region, an unusually high ratio. Researchers interpreted that ratio as evidence. This black hole may be the leftover core of an entire separate galaxy that had been almost completely stripped away, torn apart and absorbed by a larger galaxy long ago, leaving only its dense black hole-anchored center behind, drifting loose through its new host with nothing left to mark where it came from except the black hole itself and whatever stars remained gravitationally bound tightly enough to survive the process. A second, similarly strange event, catalogued as TD 2025 ABCR and studied directly using Webb alongside ground-based telescopes at Keck, showed a black hole offset by an even more extreme distance, more than 9,000 parsecs from its galaxy's center, roughly 30,000 light-years, comparable to the distance separating our own sun from the center of the Milky Way. Analysis of the debris from the destroyed star put this black hole's mass somewhere between 1 million and 10 million times the mass of the Sun, a small fraction of the mass of the actual central black hole, still sitting at the true nucleus of that same galaxy. Researchers concluded the most likely explanation was that this second black hole had been flung out of position during a past collision or merger between galaxies, ejected from wherever it originally sat and left to wander, undetectable, through the outer reaches of its new home, identified only because it happened to catch and destroy a star exactly when astronomers were watching in enough different wavelengths to piece together what they were actually looking at. Think about what that actually means. There are supermassive black holes drifting through galaxies right now with no galaxy of their own left to claim, no bright central bulge marking their location, no active feeding disk giving away their presence, completely undetectable, using any method other than waiting, by pure chance, for them to destroy something. They are not hiding behind dust the way the black holes in the earlier study were. They are hiding by simply not being where anyone would think to look, wandering loose through the outskirts of galaxies that are not even their own, silent and dark until the one moment their gravity happens to catch something too close. And light briefly reveals exactly where they have been all along. This matters for something bigger than any single discovery too, because astronomers have spent decades trying to build an accurate count, a census, of how many supermassive black holes actually exist across the universe and how they got so massive in the first place. Every black hole found hiding behind dust, and every black hole found wandering loose through a galaxy far from where anyone expected to look, is a black hole that would have been completely missing from that census, using the methods available even 5 years ago. If a meaningful fraction of the universe's supermassive black holes turn out to be sitting in either of these two categories, cloaked by dust or wandering unanchored through the outskirts of galaxies, then existing estimates for how many of these objects exist and how common galactic mergers that eject or strip them actually are may need real revision. Scientists studying intermediate mass black holes, a related but distinct category sitting between stellar-sized black holes and true supermassive ones, have separately noted just how difficult this entire class of object is to find under normal circumstances. Difficult enough that tidal disruption events, catching them in the singular act of destroying something, currently rank among the only reliable ways to confirm they exist at all. Taken together, these two lines of research point toward the same unsettling conclusion from two completely different directions. The population of supermassive black holes we can currently detect and study, sitting quietly and visibly at the centers of galaxies, doing something that shows up in our telescopes, may represent only a fraction of how many of these objects actually exist. Some are cloaked behind walls of dust thick enough to block every wavelength of light, except the infrared web was specifically built to see through. Others are not even where you would expect a supermassive black hole to be at all, drifting through galaxies far from any center, remnants of long-forgotten galactic collisions, invisible until they happen to intersect with something unlucky enough to wander into their path. In both cases, the black hole gives no warning. There's no buildup, no gradual brightening, no signal that something dangerous is nearby. There is silence for an unknown length of time, and then, without notice, a flare bright enough to briefly rival an entire galaxy, and then silence again. Researchers involved in this work are now actively using Webb's infrared sensitivity to search for more of these hidden events across the dustiest, most obscured galaxies they can identify. Work that is likely, over the coming years, to reveal even more of what has effectively been an invisible population of dormant, star-killing black holes scattered throughout the universe, sitting quietly, waiting, in places no previous generation of telescopes ever had the ability to actually see. It is worth stepping back and considering just how much this changes about a question astronomers have been trying to answer for decades: how many supermassive black holes actually exist, and where they actually are. For most of the history of this field, the honest answer has been built almost entirely on what could be directly detected: active black holes lighting up their surroundings, black holes at the visible centers of otherwise ordinary galaxies. Every method available before Webb was, in effect, only capable of finding this specific subset of black holes that were cooperating, either by actively feeding and glowing, or by happening to sit exactly where a telescope pointed at the right dust-free galaxy could actually see the aftermath of a kill. Everything else, silent black holes wrapped in dust, wandering black holes flung loose by ancient galactic collisions, existed in a genuine blind spot, a category of object astronomers knew, in principle, should exist somewhere, but had no reliable way to actually count. That blind spot is now, for the first time, starting to close, not because black holes have somehow become less dangerous or less silent, but because an instrument finally exists that is sensitive enough in the right part of the spectrum to catch the brief moment their silence breaks. Every dusty galaxy Webb examines from here forward is a chance to find another one of these dormant waiting objects, and every wandering off-center flare astronomers catch with Webb and ground-based telescopes working together is a chance to map out just how many supermassive black holes have ended up drifting loose through the universe, unanchored, following collisions that happened long before anyone was watching closely enough to notice. None of this changes the actual danger involved either, at least not in the abstract sense that matters to astronomers studying it from a safe distance of millions of light years. A star that wanders too close to any of these objects, dormant or active, anchored or wandering, dust-shrouded or clearly visible, ends the same way, torn apart, stretched into a stream of glowing debris and slowly consumed. The only thing that has changed is our ability to actually see it happen, and to recognize, after the fact, that something had been sitting there all along, waiting in the dark, doing nothing detectable, until the one moment it very much was not doing nothing at all. If this is the kind of story you want more of, subscribe and let me know in the comments whether you think there's something like this hiding closer to home than we'd like to admit.